So I want to start by telling you what I'm going to talk about today, and then I'll go back and go through the details. But the points I'm going to be making, the major problem is the complexity today is reaching a new level where old approaches are becoming less effective and new causes of accidents are appearing. I believe we need a paradigm change. We need to change from our focus from increasing component reliability to enforcing safe behavior. Excuse me, using dynamic control. If we do this, it will allow us to create new analysis and engineering approaches that are more powerful and inclusive, that are orders of magnitude less expensive, and that handle very complex systems using top-down system engineering methods. We found recently that this new paradigm applies to security too, and in fact, any emergent system property. The final thing I'm going to talk about is, does it work? It may sound good on paper, but does it really work in practice? And there have been many evaluations and much experience with it in real life, and so far it shows that it works much better than what we're doing today. So let's start with what we're doing today. Our current tools are all 40 to 65 years old, but our technology is very different today. Do I have a pointer? So if you look here, you see FMEA goes back to failure modes and effects analysis goes back to 1940s. Fault trees to the 1960s, and in fact, everything we do today really goes back before 1970. But our technology has changed tremendously since then. We are now are introducing computer control in everything. There have been exponential increases in the complexity of the systems we're building, and lots of new technology. But notice, these things were all developed before any of this happened. And in fact, software has revolutionized engineering. The role of software in accidents almost always involves flawed requirements. What happened to my, oh, there we go. Sorry, I knew something was missing. The first point is that software does not fail. All of our techniques for reliability and for safety assume that things have failed. But software is something very unique that we never had before. And in fact, what is really software doing? Well, software is the design of a machine. We put the software onto a general purpose machine and we get a special purpose machine. So if we put the design of an autopilot on a general purpose computer, we get an autopilot. But using that same general purpose hardware, if we put the design of an inventory control system, we get an inventory control system. This is something we have never, this is why past software is so powerful. We have never been able to do this before. Software is simply the design of a machine abstracted from its physical realization. Its essence is pure design. We've never had that before. But what does it mean for pure design, an abstraction, to fail? It's just design. It has no physical presence. The second problem is that the role of software in accidents almost always involves flawed requirements, either incomplete or wrong assumptions about the operation of the control system or the required operation of the computer, or unhandled control system states and environment. In fact, we often spend, what happens is, for example, the autopilot provides some requirements to the software engineer, and the software engineer then designs the autopilot. The problem is we spend most of our effort here on making sure that the implementation is correct. But almost all accidents, I've been doing this for 35 years, and virtually every accident, and I've seen hundreds of them, every accident has involved flaws in the requirements, not in the implementation. So merely trying to get the software correct or to make it reliable is not going to make it safer if the requirements are wrong or are unsafe. The third problem is that software allows almost unlimited system complexity. We can no longer plan, understand, anticipate, and guard against all undesired system behavior. We used to be able to test our systems, usually often exhaustively, and get the design errors out. And so all we had left were component failures, random failure, when we were using the systems. But this is no longer true. Our systems are so complex that we cannot test to find all the errors. So we now have two types of accidents. The first type is the old traditional component failure accident, where there are single or multiple component failures, and we usually here assume some kind of randomness in the failures. But we now also have increasingly seen component interaction accidents that arise in the interactions among the components. None of the components may have failed. It's really a system design problem. They're related to interactive and dynamic complexity in the systems that we're building. It's only a random failure, sir. It'll never happen again. Here's an example of an accident with no component failure. It was the Mars Polar Lander that crashed into the surface of Mars when it was landing, and we lost it. Now, in this system, the spacecraft comes in very, very fast. So it has to slow it down before it can land on Mars. And how do they slow it? Well, they use the Martian atmosphere, although it's not a lot of atmosphere, so it's not too effective. They use a parachute in this specific spacecraft. They use a parachute that they extend to slow it down. And they also use these descent engines. There are engines controlled by the software which push against the direction of the spacecraft to slow it down. Now, when it lands, the descent engines have to be turned off quickly, because otherwise it'll go pushed back up and come down and crash. So there are some very sensitive sensors in the legs of the spacecraft, sorry. And when they get the software engineers were told that when they get any input from one of these sensors, they should immediately cut off the engines. And it did that. But there's a problem. When the parachute opens, there's a jerk on the spacecraft, and there's some noise signals, some false signals that are generated. Now, that wasn't in the software requirements. They didn't tell the software people about it. We're not quite sure why they made this mistake, but it's a common mistake. But maybe they made it because the software wasn't supposed to be operating when the parachute opened. It was supposed to, software was going to start operation later. But the software engineers decided to start the software early in order to even out the load on the processor. And so it got these false signals. It assumed that the spacecraft had landed, and it shut down the descent engines above the surface, and it went crashing down to the Mars surface. Now, if you look at this, you see nothing failed. Each component worked exactly the way its requirements specified it should work. The problem was in the overall design of the system, of the spacecraft, and the inability for engineers to see all the different things that could happen. So there's often a confusion between safety and reliability. So in the green circle are unreliable but not unsafe scenarios. Those are all the failures that can occur, failure scenarios. And this circle are the kinds of things that FMEA, failure modes and effects analysis, identifies. The pink circle is all the unsafe scenarios. Now, in the overlap, they're unreliable and unsafe. That's what fault tree analysis finds. But this part over here that are unsafe but not unreliable can't be found by our techniques, which are basically reliability techniques, techniques that are looking for failures. The final really big change with software is that the role of humans in systems has changed. There's usually always been an assumption that operator error is the cause of most accidents and incidents. So as soon as the plane crashes, before they've even gone and found the plane, it's always announced that it was pilot error. Or most of our accidents in automobiles are assumed to be driver error or driver fault. So if that's true, then we have to do something about the operator. We could admonish them, fire them, retrain them, but we have to do something about them. Or we can do something about operators in general. We can marginalize them by putting in more automation. So we put more automation between the driver or the operator and the actual physical system they're controlling. Or we rigidify their work by creating more rules and procedures that they probably won't be able to follow. Fumbling for his recline button, Ted unwittingly instigates a disaster. All human behavior is affected by the context in which it occurs. So operator error in a systems view of accidents, the new view of accidents, is that it's a symptom not a cause. It's a symptom of something wrong in the system design. For example, today, the role of operators is changing in software-intensive systems, as is the errors that they make. We are designing systems in which operator error is inevitable, and then we blame the accidents or the systems on the operator. So to do something with this new view of error, to do something about operator error, we have to look at the system in which people work, the design of the equipment, the usefulness of the procedures we give them, the existence of goal conflicts, production pressures to work faster. Human error, bottom line, human error is a symptom of a system that needs to be redesigned. So if we say that the accident caused is human error or operator error, we've learned nothing. We have to understand why people who are well trained, usually, trying to do the right thing, do the wrong thing. It's not just a random thing. It's usually something about the design of the system. And in fact, today, we too often have human factors people concentrate from the screen, the interface screen, outward. So we look at the screen design, they look at the training of the operator, they look at the procedures, and engineering concentrates only on the screen in. The problem is that there's not enough attention on the integrated system as a whole. So we're designing automation that's confusing the operators. Mode confusion is very typical today. The operators are confused about what mode the aircraft or the automobile is in. Or situation awareness. They're confused about what's happening in the system. So we need to figure out how to do better integrated design. In engineering now, there's this usually called human system integration. It's still hungry, and I've been stuffing worms into it all day. Everyone's trying to do the right thing, but they're using the techniques that they used for the old problems they used to solve. The problem has changed, and so we end up feeding worms to the babies, trying to do the right thing, as I said, but not doing something that's very useful. So I believe we need something new. We have new levels of complexity, software, and human factors that just don't fit into a reliability-oriented world. We are trying to shoehorn new technology, force new technology, and new levels of complexity into the old methods. And it's not working. So what's the alternative? Well, I believe the alternative is to use systems theory. The problem is complexity. That's the problem we're trying to deal with. People are not going to stop using software or stop building complex systems. So we need another solution. Traditionally, there are 3 ways to deal with complexity. One is something called analytic reduction. The second is statistics. And the third is systems theory and systems engineering. Analytic reduction goes back to Descartes, very old. 200 years at least. And what they did was and said was that if we have a complex system, what we should do is divide that system up into pieces so that we can analyze the separate pieces. So the physical aspects are separated into physical or functional components, and behavior is divided into events over time. Then what we do is take these separate parts, examine them carefully, analyze them, and then combine the analysis results later. There's some assumptions here. It assumes that that separation doesn't distort the phenomenon itself, that each component or subsystem operates independently, that the components act the same when we examine them singly as when they are playing their part in the whole, and that the events aren't subject to feedback loops and nonlinear interactions. And for many systems, those are reasonable assumptions. And so we based our traditional approach to safety on this reductionist idea. Divide the system into components, assume that accidents are caused by component failure, identify chains of directly related physical or logical, that is, functional component failures that can lead to a loss. And that's what we're doing in fault trees, right? You're looking at put it together in a tree, but it's really a chain of events that you're identifying, failure events. And then we evaluate the reliability of the components separately, and later combine the analysis results into a system reliability value. The problem is that this assumption of randomness in the failure events is required to derive the probabilities for a loss. But software and humans don't satisfy that assumption. Software and humans don't behave or fail randomly. In fact, they don't necessarily fail. But this idea of accidents as chains of failure events forms the basis for most safety engineering and reliability engineering analysis, fault tree analysis, probabilistic risk assessment, failure modes and effects analysis, event trees, fault hazard analysis, and so on. And it also forms the basis for our design techniques. We concentrate on dealing with component failure, because if component failure is the cause of all accidents, then we need to design to protect against component failure. We use redundancy, barriers to prevent failure propagation, high component integrity, over-design, build-in safety margins, fail-safe design, and for humans, we identify operational procedures, checklists, provide training, and so on. The problem is, it doesn't work for a lot of things. It doesn't handle these component interaction accidents where there were no failures. It doesn't handle system design errors. It doesn't handle systemic factors that affect all the components in the barriers. It doesn't handle software and system requirements errors. It should be system. It doesn't handle human behavior in anything but a very superficial way. It doesn't handle indirect and nonlinear interactions and complexity. And it doesn't handle the migration of states toward higher risk over time. In the search for greater efficiency and productivity, we start to change our behavior, and we usually move towards states of higher risk. You don't have an accident, so you think, oh, well, we can make it more efficient. And you keep doing that until you eventually have an accident. So the alternative to this is systems theory. So I want to spend a few minutes defining systems theory, because although it's very old, it's not taught very often in universities. It was developed for systems. Actually, it was developed in the 1940s, 1950s, for systems that were too complex for complete analysis, that when you separated them into separate systems, it distorted the results. And the most important properties in this system are emergent, and I'll explain what that means, but basically they emerge from the interactions between the components. At the same time, these systems were too organized for statistics. There's too much underlying structure that distorts the statistics, and in fact, new technology and designs have no historical information. If you've written the software and it's the first time it's being used, which is usually the case, how do you know what the probability of failure, if we even can define software failure, is? We have no information until 10 years from now, and then it's too late. In fact, systems theory was first used in the 1950s and 1960s for the intercontinental ballistic missile systems that the United States was building. We started having accidents, and these systems were so complex, they started having these component interaction accidents. They started having accidents where nothing individual components failed, but it was in design errors caused by system design errors. And in fact, system theory became the basis for system engineering. System engineering was also invented for these same ICBM systems and system safety at the same time. So what is systems theory? Well, it focuses on systems taken as a whole, not on the parts taken separately. It looks at things that I mentioned before, emergent properties. These are properties that can only be treated adequately in their entirety, taking account all social and technical aspects. You've probably heard the phrase, the whole is greater than the sum of the parts. That's the basic principle behind systems theory and behind system engineering. These emergent properties arise from the relationships among the parts of the system, how they interact and fit together. So let me give some examples. First of all, this is all of the components of a complex system today, really complex today. But that doesn't tell you how they interact. So here's a diagram showing that we have a process. It has components. The components interact in direct and indirect ways. And as they interact, they produce these emergent properties. They arise from the complex interactions between systems. Safety and security are emergent properties. If I hold up a valve and I tell you, I'm going to use this valve in my car or in my nuclear power plant, will the car or the nuclear power plant be safe? You can't answer that question because safety is not in an individual component. It's in how all the components interact together. So how do we deal with emergent properties? Well, we need some way to control the interactions. We actually need to control two things: the individual component behavior and the component interactions. In essence, we're enforcing constraints or safety constraints on the interactions or the behavior of this system. As an example, if every plane in the air decided it would optimize its own path from takeoff to landing, we would have chaos, and we'd have accidents, because we might have all the planes wanting to land at Narita at 5 p.m. And so we have to somehow, and then nobody gets optimized. So each of them trying to optimize their own path means that the whole system isn't optimized. Nobody gets to where they want. So we put in an air traffic control system. The air traffic control system controls where the planes go. It optimizes the overall safety and the overall throughput, but not necessarily each individual plane's path. Okay? But system-wide, that's what we mean by an emergent property. It has to be controlled in some way. Now, there are lots of other emergent properties: producibility, quality. And these actually, when I'll get to this at the end of the talk, the same process will work for these other qualities, and we're starting to show that. People are starting to show that. So this controller has to issue control actions to control the behavior of the components, and it gets feedback from the system to find out what's happening in it. So I mentioned safety constraints. These are examples of safety constraints. Power must never be on when the access door is open. 2 aircraft or 2 automobiles must not violate minimum separation. Aircraft must maintain sufficient lift to remain airborne. The integrity of the hull the outside must be maintained on a submarine. Toxic chemicals and radiation must not be released from a plant. Workers must not be exposed to workplace hazards. Access to information must not be allowed to unauthorized people. These are all the high-level functional requirements to address during design. They're what your system must enforce in order to be safe or to be secure. Now, this is a very broad view of control. Component failures, which we still have to deal with, and unsafe interactions may be controlled through design. Redundancy, interlocks, fail-safe design. We're not omitting anything here. We're adding to what we already do. Or through process, engineering processes, manufacturing processes and procedures, maintenance processes, operations, or through social controls, government or regulatory controls, culture of an organization, the safety culture. Insurance companies are very effective controls. Law and the courts, individual self-interest. You design an incentive structure that encourages people to do the right thing. There may be multiple controllers, multiple levels of control. Each controller enforces specific constraints, which together enforce the system-level constraints or emergent properties. And so just an example, we have communication also between these things. So here's a very small example, sorry. But right down here is actually the physical process. Above that, we may have an automated controller. Above that, a human controller. And this in the red box is the operating process. But above this, in the operations control structure, there's operations management, company management, government regulatory agencies, industry associations, insurance companies, the courts. Above that may be some legislative branch of government. Between each of these, there's a feedback control loop. The company management, for example, provides safety policies, standards, resources, and gets back reports or feedback about how things are going. Over here, the same thing with system development. We have a control structure. We have information going between the two. Let me show you a little example of this operating process here. We can just look at that. This is an adaptive control system, and the brake control module for one in an automobile. Simplified diagram. We have a driver that uses some instruments to send messages and control action to the adaptive cruise control module. The adaptive cruise control module sends a braking signal to the brake control module, gets back feedback in terms of braking status, vehicle speed. The brake control module sends a signal to the brake, which uses friction to stop the vehicle, and gets feedback about the wheel speed. All right, this is just, most of you are probably engineers, and you've seen something like that. It's just a standard feedback control loop. But we're going to use this for our analysis, our safety analysis, instead of failure diagrams. We can also look above it if we want. So for example, mechanics and repairs. Here's the operating, because we just saw the adaptive cruise control. We have the manufacturing, we have Department of Motor Vehicles, local government, highway commissions, and so on. All is part of this large safety control structure. One more example. This is a Japanese system, the HTV spacecraft that takes cargo to the International Space Station. The HTV comes up to the space station. It's grabbed by the robot arm, pulled in, unloads its cargo, and then leaves. When it's near the space station, it's very dangerous for it if it hits the space station. Now, just an example of the control structure, and to show you we can do control structures at levels of refinement. At the very top level, we have a simple control structure. This is the International Space Station. Here's the HTV. This is a backup means of communication. We have NASA ground station. We have JAXA ground station. And to avoid certain kinds of problems, JAXA can only talk to NASA, which talks to the astronauts. Otherwise, we sort of had chaos with different instructions being given to the astronauts. Now we can look and we can refine this. So let's look inside the ISS. We have the crew, which controls, this is the control panel for the system. This is the monitor or feedback channel. This is the arm, the robotic arm that the crew manipulates. We have some software here, and we have things going down to NASA ground station and so on. Okay, now each of those components has some safety constraints. Those are just the assigned responsibilities, authority, and accountability for what they're supposed to be doing for safety. And they also have some controls that they can use to enforce the safety constraints. Each component's behavior is influenced by the context in which it's operating and by knowledge about the current state of the process. Now, there's one other thing that we need here, and that's the idea of a process model. Every controller has some kind of control algorithm, but it also has a model of the process it's controlling. It can't make decisions about control actions without knowing what state the controlled processor is in. We can sometimes do pure feedback control, feed-forward control, for those of you who are engineers, but normally not. Only that. This process model is often involved in accidents when a human controller or software controller is involved. So when the process model becomes unsynchronized with, inconsistent with the real state of the process, bad decisions may be made here. So for example, in the Mars Polar Lander that I told you about, nothing failed, but what happened was the software, because it got those bad signals, false signals, thought that the controlled process, the spacecraft, had landed, so it issued a command to shut down the descent engines. In fact, that's a much better model of why humans or software make mistakes or operate in a complex system than they just failed randomly. This isn't a random failure. This was a design error. There are 4 types of unsafe control that can be provided. We may not provide a control act, not providing a control action leads to a hazard. Let's use air traffic control. 2 planes are coming at each other, and there is no control action issued to make them change their direction. That's unsafe. Another thing that might happen is to providing an unsafe control action. They aren't going to hit, but control actions are issued that make them hit. We provided the right control actions, but too early, too late, or out of sequence. And finally, we stopped too soon or continued too long for continuous control. So we tell the pilot to go up to 25,000 feet, but the pilot stops at 20,000, and there are other planes there. Now what we're going to do, and I'm not going to go to the details here, I'm going to go an example in a few minutes, but this is a more detailed control loop. We have a controller, an actuator, sensor, and then the controlled process. And what we're going to do is do our hazard analysis, our safety analysis, using all the pieces, things that can go wrong anywhere in the control loop. you'll notice one of the things is in the control process, there can be component failures. We want to still do what we did before, but it's just one part of what we're going to do. Okay, so what is STAMP? STAMP stands for System Theoretic Accident Model and Processes. Instead of defining safety as a failure problem, it defines safety as a control problem. It applies to very complex systems. We have used this, or people have used this on some of the most complex systems on Earth today, successfully. We would never have been able to use fault trees, failure modes and effects analysis, or anything else on these systems. It includes software, humans, new technology. It's based on systems theory and systems engineering. And what it basically does is not replace the traditional model of accident causality, but expands it. It's not just the chain of directly related failure events, but that losses are more complex processes. So we're not losing anything, we're adding. When we treat safety as a dynamic control problem, then the events that occur that lead to the accident are identified as a lack of enforcement of safety constraints in system design and operation. That's what they result from. The goal then is to control the behavior of the components and systems as a whole to ensure that the safety constraints are enforced. It's a change in emphasis. Instead of focusing on preventing failures, we instead say we try and focus on enforcing the safety constraints on system behavior. That's going to include preventing failures, because sometimes failures can cause safety constraints not to be enforced, but it includes more than just failures. It changes our analysis goals. In hazard analysis, instead of looking for chains of failure events that lead to the accident and trying to identify their probabilities, instead we look at the ways the safety constraints might not be enforced so that those things can be eliminated or mitigated in the design or in operations. When we're analyzing an accident, instead of looking for what failures led to the loss and who was responsible, instead we say, why wasn't the safety control structure, the safety management system, adequate to prevent the loss? So using STAMP as it's not a tool, it's not a method, it's a model, a causality model. But using that, we can build tools on top of it and then put those tools together to get better processes. Some of the tools we've created are CAST, which is used for accident or event analysis, hazard analysis, which is STPA, early concept analysis. We can look at a system in the very, very early stages before we have any design. We're just building a concept document and do safety analysis on it. Organizational cultural risk analysis. We can identify leading indicators of risk increasing, and we can do security analysis with a very similar process to STPA. Our real problem is that 70 to 80% of safety decisions are made in concept formation stage, early when we're designing a system. But the techniques, so here's concept, requirements, design, this is effectiveness and cost. Most of our techniques that we have now all require that there be a design. This is the cost of design changes. Almost, actually it's probably too high, it's almost nothing at the beginning, but as we get farther in the design process, it costs an enormous amount to do rework and to make changes. At the same time, our ability to impact cost and performance goes down the farther we get into the whole development process. So what we need is something up here. And STPA, which I'll talk about, and STPA, which I'll talk about, are two new tools that work very early to help us design safety into the system before we've made irreversible design decisions that turn out to be wrong or not very wise. So let me start with STPA. It's a top-down system engineering analysis techniques. It identifies the safety or whatever emergent property you're looking at, constraints, that is, it identifies the system and component requirements. It identifies the scenarios leading to the violation of the constraints or requirements, and then we're going to use that information to design or redesign the system to be safer. It can be used on technical design and organizational design, and it supports a safety-driven design process where the analysis influences and shapes the early design decisions, and the analysis as it's iterated and refined as the design evolves. So as we make design decisions, we'll iterate and refine the analysis in parallel. So here's another example that I'm going to use. I'm going to show you STPA on. This is a real accident. It occurred in England. It was a batch chemical reactor. The computer was responsible for opening and closing a valve that allowed catalyst to come in and start the reaction. The computer also controlled a water valve that allowed cooling water to go into the reflux condenser and cool off the reaction. Now one day, it had one other requirement. They were told, the software engineers were told, there were some sensors in the plant. And the software engineers were told, if you get any input here, it means something has gone wrong in the plant. What you should do is stop everything, sound an alarm, and tell the operators. So one day, there was a low oil level in a gearbox. And the computer got word of that, and it stopped everything, and it sounded an alarm. It did exactly what it was supposed to do. So nothing failed here, but it turned out that this information came in just after the computer had opened the catalyst valve, but before it had opened the cooling water valve. So while the operators were at the gearbox putting in more oil, the catalyst overheated, the reactor overheated, vented vapor up through a vent and out into the neighborhood for all the people to breathe. Now again, notice nothing failed here. Every component worked the way it was supposed to work. The problem was a design error. In the requirements, they never told the operator, the computer programmers, that to open the cooling water valve before they opened the catalyst valve. If they'd told them that, they probably would have done it right. They just didn't know. That's the kind of thing we're having here with this related to software. So how are we going to analyze that with STPA? I don't have time to teach you STPA, but I will show you an example of how we do it. The first thing is you have to build a functional control structure. Here's the physical model that you saw. It's the physical interactions between the components. But it's not the logical interactions. So we build this functional model, which has three components: the operator, the computer, and the valves. And we need to know who controls what commands are sent, and what feedback is provided. Well, the operator controls the computer controls the valves. The commands set by the operator are start and stop. It gets information back about the plant status, the alarms. The computer can open or close the water valve, and it can open or close the catalyst valve. We may not know what feedback we need, but in the analysis, we find out what feedback is needed for safety. The next step is we have to say, how could unsafe control be provided here? Well, I said earlier there are 4 ways unsafe control can happen. Providing the control action leads to a hazard. Not providing the control action leads to a hazard. Timing or sequencing leads to a hazard. Duration. So what we're going to do first is identify the conditions under which the control action can lead to a hazard. Then we're going to use that information to try and discover why could that happen and design it out of the system early. So we use a table. Actually, Jackson engineers came up with the idea of using the table. So this is a Japanese invention. Here's the control action and then the 4 types of unsafe control. So let's start this. We're going to look at the computer. It can open the valve, water valve, close the water valve, open the catalyst valve, close the catalyst valve. What we want to do is, we want to provide them. They have to do this. We provided those instructions for good reason, but we need to determine when they can be unsafe, under what conditions. So what about opening the water valve? Can not providing it cause a hazard? Well, yes, if it's not opened when the catalyst is open. Can this be unsafe, providing the open water valve command? Are there any conditions under which it's unsafe? Can you think of anything?
Time or duration is one of those conditions which could lead to hazard.
Yeah, they can, but not this provided. What it means is we could waste some water. But opening the valve doesn't do anything but waste water. It doesn't cause overheating of the reactor. But if we open the water valve more than X seconds after the catalyst valve, or we stop opening the water valve before it's fully opened, then we could get overheating of the fuel, which is the hazard. Now we can fill in the rest of these. Do I have enough? I don't think I have enough time. It's going to make you do it. But I'll show you it. Closing it while the catalyst is open, closing the water valve. You know, I forgot that when I first started thinking about this. I thought, well, I just have to open the water valve before the catalyst valve. But I forgot that if I close it before I close the catalyst valve, I could have a problem. So you just fill this in. There are lots of them. We don't have to go through it. You'll have it in your notes. You can look at it if you want. And we can take this information and write requirements, high-level requirements for this reactor, software requirements. The water valve must always be fully open before the catalyst valve is open. The water valve must never be opened or completely opening more than X seconds after the catalyst valve opens. The catalyst valve must always be fully closed before the water valve is closed. So we just identified the requirements for the software. Remember, most accidents in software, virtually all of them, are caused by bad requirements, flawed requirements. We can use this to identify those requirements. There's no other technique that can do that. But there's more. Oh, first of all, we can automate much of this. John Thomas figured out how the engineer can just provide the hazards and the computer automatically fills in that whole table for you and then generates formal model-based requirements directly from the hazards. Because there's an underlying discrete mathematical model, we can do automated various kinds of checks, detect inconsistency, incompleteness, and so on. The next step, people stop here, but you're stopping too soon. We need to go on. We need to identify why would those things happen? Why would the computer open the catalyst valve when the water valve wasn't open, for example? Why would it do that? So we need to identify the causal scenarios of the unsafe control actions, including why the process model might be incorrect, and also identify safe control actions being given but not executed. So the computer could do the right thing. It could issue an open water valve, but the water valve may not open. Those are the standard kinds of failure scenarios identified by FMEA and by fault trees. We still need to do those things, but they won't identify this first type. And then the next step is to look at what design features or controls might you use to protect the system from the scenarios that you found. So here's an example. Let's say our unsafe control action is that the software issues an open catalyst command when the water valve is closed. Why would it do that? Well, no one may have told the software engineers about it, which is what actually happened. Or probably if you used STPA, they got that information. But the software may think the water valve is open, so it issues an open catalyst. Right? It thinks that the water valve's open, so it opens the catalyst valve. Why might this, and that's really because the process model is incorrect. Why might the software process model think that the water valve is open when it is not? Well, there are lots of scenarios. Here are some examples. If the software issued an open water valve command, but the valve didn't open. It was jammed, it was failed, etc. But the software assumes because it issued the command, it was executed. Well, hopefully as engineers you immediately see that the problem here was missing feedback, right? If we got some feedback, it would know it hadn't opened. In fact, that's so typical in air that it happened at 3 Mile Island. It happened in dozens of accidents where a command was issued to open a valve. It got some feedback actually, but the feedback was wrong because all it did was look at whether the command got to the valve, but not whether the valve actually opened. All right, so it assumed the command had been executed. Why? Well, there's no feedback, as I said. The control put feedback in. The feedback wasn't received. We could go on to determine why the feedback wasn't received, or, and this is one of the good things about this, you don't have to get all the details. All you need to do, because you're doing a top-down analysis, you only need to get as much information as you need to figure out how to control the problem. So we may not need to know why the feedback wasn't received, but just assume that if you don't receive it, tell the software, if it doesn't receive feedback, assume it wasn't executed and issue it and do something. And we'll have to figure out you'll have to tell it what you want it to do. The feedback could be delayed. Again, we could determine why, or we could issue a requirement to the software to wait some predetermined time and then assume it wasn't open and do something to account for it. Or it may have received incorrect feedback. Why? Well, maybe it assumed, and this is the one I talked about, if it reached the command, if it reached the valve would open. But that's not necessarily true. That's, again, what happened at 3 Mile Island. So what can we do? Well, we can add a flow meter to detect that water is really flowing through the pipe. There are other solutions. All I'm showing you here is if you understand why things could go wrong, really bad things could go wrong, then we can figure out how to design to protect against them. So this generates new requirements. We didn't finish with just those first requirements from the table. We have to go on to get more detailed requirements. So requirements to include feedback. The software shall check for feedback after issuing an open-close command. If not received in a specified time period, then assume that the valve is not open or closed and do something. What you do will depend on what the system's doing. There must be feedback to the controller to determine that water is actually flowing through the pipe before issuing an open catalyst command. Perhaps you could write a more detailed requirement and say use a flow monitor or use something. But what we're doing is, as we're designing this thing, we're figuring out what could go wrong that would be hazardous, and then designing in a fix for it. There's one other thing. I said we need to consider that the command was provided but not executed. That's traditional kind of things that you look in a traditional failure analysis. But we may be able to solve the problem without going through all the way it fails. We just may be able to figure out some other design solution and save ourselves a tremendous amount of time. I just want to make a comment. Our analysis can include the human operator. The analysis works the same way for humans as it does for software. And we have lots of examples. I don't have time to show one. But you can now treat the operator as part of the system without sort of separating them out and not considering them. That's STPA. I'm going to go through the other tools much quicker. TAST is an accident analysis technique. It helps in understanding the entire accident process and identifying why it occurred. We get away from blame and shift the focus to why and how to prevent it in the future. Our goal is to determine why the people behaved the way they did. If you stop in your accident analysis and you say, pilot pulled up when he shouldn't have, you haven't learned anything. There's some reason why the pilot pulled up when the plane was didn't pull up when the plane was in a stall, for example. These are trained pilots. They didn't just have some random mind warp or something. They usually did it because they thought that was what they needed to do. So we need to look at why did they think it was the right thing to do. And then we can help provide a better design and better information to the pilots or the drivers of an automobile. STPA is a brand new technique. A PhD dissertation was finished in January. It's already being used. Most of my students' PhD dissertations are used before they can ever get them published or finish them. This one's wonderful. It works really early in system design. When you only have an English language concept of operations, you don't know anything, we can take STPA, create a model of the early system, and use model-based analysis to identify unspecified assumptions, missing, inconsistent, incomplete information in your concept of operations document, vulnerabilities, risks, trade-offs, system, software, human requirements, and architectural and design analysis to eliminate and control the hazards. So for example, this is going to be very quick, but this is something called TBO, trajectory-based operations. It's part of NextGen, which is the upgrade to the air traffic control system in the United States. TBO is extremely complicated. We're basically doing everything by computers, getting rid of radars, using satellite navigation. It's really, and people will be able to take direct routes instead of going around in a long way. So far, all they have is some English language concept of operations. That's all they've gotten so far, because they don't really know how to do this yet. So taking that English, Cody Fleming, Dr. Fleming, figured out a procedure for creating the control loop that's implied by that language. And when you do all this, you get a control loop and you immediately see things missing. Like, here's a control loop that isn't closed. or you see missing feedback, or you ask other questions, like we have 2 conformance monitors, one in the air, one on the ground. How are those going to be kept consistent? And so on. So we use this to analyze our concept of operations. And in fact, the properties have been defined formally. So we can identify gaps in responsibilities, conflicts in responsibilities, coordination problems, inconsistency problems, and you don't have to worry about the math. The point is that we've defined it formally, and therefore potentially much of this can be automated. The analysis. All right, that's STPA. What about cybersecurity? Well, there's an Air Force colonel who was my student, Bill Young, who decided the STPA worked for security. And I said, I don't believe it. I said, show me. So he did. Currently, cybersecurity doesn't work today. I mean, I'm sure I got mail this morning that I was one of the 5 million people that the Chinese stole all my security information about. And the Chinese know all about my background now. It's not working. We're hearing about more break-ins every day, and they're getting worse, not better. Something's not working here. And what he argues is that now we're focusing on tactics. We often frame cybersecurity as a battle between adversaries and defenders with tactics. And it requires correctly identifying the attacker's motives, capabilities, targets. That doesn't work. Now, he's in Air Force, and the Air Force, the people in the military know, you can't just use tactics. You need strategy to control the tactics. So we can reframe the cybersecurity problem in terms of strategy. We want to identify and control system vulnerabilities rather than reacting to potential threats. It's a top-down strategy versus a bottom-up tactics approach. It's a system engineering approach to security. The tactics are going to be handled, but they're handled later once we understand the problem we're trying to solve. So we can have an integrated approach to safety and security. They're both emergent properties. The STAMP model of causality works for security, both cyber and physical security. We're doing that too. It starts with identifying the unacceptable losses. What are the essential services to be secured? What is used later to reason thoroughly about how best to guard against the threats? The analysis essentially moves from the general to the specific in a top-down system engineering approach. Here's an example, Stuxnet. Stuxnet was the virus that somebody, most likely the US, put into the Iranian reactor to delay their being able to process radioactive fuel, and get a bomb or nuclear weapons. And here the loss was damage to the reactor, in case the centrifuges. What this virus did was it made the reactor centrifuges turn faster than they should, so they kept wearing out. So the Iranians had to keep, it was very clever actually, they couldn't figure out what was going on. They just kept replacing these centrifuges, but they weren't getting anywhere in their program. So the hazard is that the centrifuges are damaged by spinning too fast. The constraint is the centrifuges must never spin above a maximum speed. The unsafe control action here is issuing an increased speed command when they're already spinning at the maximum speed. Now, it doesn't matter whether that was intentional or whether it was accidental. We still have to deal with it. One potential causal scenario might be incorrect process model. It thinks it's spinning at less than the maximum speed. Again, that could be inadvertent or advertent. What are potential controls? Well, a mechanical limiter or an interlocker or an analog RPM gauge. We can put physical hardware controls in here that would protect against all this cybersecurity nonsense. And so we solve the problem without having to figure out every way that this and protect ourselves could be attacked. What we're really doing is, security is even worse than safety. Usually, we react only at the end when we're operating the thing and something happens. At best, we add some kind of bolt-on after we've built the thing, some kind of add-on to the system design. What we really want is to design this stuff to be safe and secure from the very beginning. Instead of playing this little game where we wait for them to attack and then we try and fix the hole, and then they find the hole in the hole, and we get nowhere. Or we try and predict every attack that they could possibly do. Can't be done. This stamp and all these tools apply to other applications. And in essence, it applies to any emergent property. In fact, right now, I've just started working on something I never thought I would work on, which is occupational or workplace safety with Boeing. Boeing is concerned they're speeding up their production lines and are concerned about injuries in the production lines. We're using this to actually reduce injuries to workers in manufacturing. We can use it for risk management, identifying leading indicators. Some examples of things people have done: risk in a software quality organization. That's at Lawrence Livermore National Labs. CO2, carbon dioxide capture, transport, and storage. Some people in France did that. U.S. Coast Guard financial management. People are using this in the financial world. Never thought that would happen. But they tell me it works. Aerospace, producibility risk management, analyzing sources of quality loss and engine technology changes, identifying feature interactions in automobiles. One of the big problems in automobiles, we have so many features, we add a new one, and it interacts in ways that people never anticipated. There are 100 million lines of software on an automobile today. Trying to figure out how you're going to keep these from interacting with each other when you add something new in some unexpected way. For example, just GM, probably no one from GM here. GM just had a major recall where if you put too many keys on your keychain, it would disable the front passenger airbag. Why? I mean, who would have thought that is a very obscure interaction? Does it work? This is the next question. Is it practical? It's being used on nearly everything, every kind of industry. This is just some of them, but it's been used everywhere now. Whatever you're in, it's probably been tried on. The question then is, well, they've used it, but did it work? Well, many of these systems are very complex. For example, the new U.S. missile defense system, in which it was used before deployment, and they found so many paths, the inadvertent launch, that nobody had found earlier, that they had to delay the system for 6 months and spent hundreds of millions of dollars fixing just the things that two people I know found in 4 months on this thing. In all the cases where a comparison has been made, and most people are comparing it with their old techniques, STPA found the same hazard causes as the old methods, plus it found more causes than the traditional methods, usually those related to human error and related to software. In some evaluations, it found accidents that had occurred that the other methods missed. The analysts weren't told, were given this was in a nuclear power plant, a medical device has happened too. They were given a design, just told to analyze it, and it turned out there had been an accident related to that system, but the analysts didn't know about it, and only STPA found them. The cost, this was surprising, was orders of magnitude less than the traditional hazard analysis methods. I assumed that it would cost a lot more because it's so much more powerful. It's much shorter. So for example, on one medical device, this is something that was recalled because it killed someone. They had done a FMEA, failure modes and effects analysis, on it, and it had taken a team of people about a year to do it. One graduate student at MIT who was just learning STPA did STPA on it in 2 weeks. The FMEA found 75 scenarios to accidents. STPA found 175 scenarios and found the one it turned out this device had been involved in an accident and been recalled by the US government. And it actually found 9 scenarios leading to that accident. So it's working. The same thing as cybersecurity. The US Department of Defense is evaluating STPA for security on real Air Force and military missions. And it was so much better, but with real experts, real cybersecurity experts. And STPA was so much better, they have now issued policy for everyone in the DoD to use it for certain kinds of security problems. So, summary. It's a more comprehensive and powerful approach to safety and security or any emergent property. It includes social, organizational, operator, software-related factors. It's a top-down system engineering approach. It starts at the very beginning. You can design the safety and security and the other properties in from the beginning. And it handles much more complex systems than traditional safety analysis approaches, and it costs less. So, what's happening? Well, the event-based thinking, the traditional things that look at failure events, see only one part of the iceberg. When we use STAMP and systems thinking, we see all these additional things that aren't visible otherwise. Thank you.